In this video, I'm going to discuss the topics of limits and derivatives as we prepare for our final. First, I want you to draw your attention to this graph we see on the right. And as we evaluate a limit from the left and from the right, what we are looking at is what the graph approaches. So if I were to ask you to find the limit as x approaches, let's say 0 from the left, basically that means as I am coming in on my graph from the left, what y value am I approaching? And in this case, I'm approaching a y value of -1. I don't equal -1, but that is what my graph is approaching. Now, if I were to look at the limit as x approaches 0 from the right, I would now be coming in on this direction. And as I come in from the right, my graph is now approaching 0. Now, this would be an example right here of where the overall limit doesn't exist. So if I were to look at this graph and say the limit as x approaches 0, in this case it would not exist because the limit from the left and the limit from the right are not equal. Now if the limits approach the same value, then the limit exists. So if I were looking at my graph, I could say, for example, the limit as x approaches 1 would be equal to 2, because as I approach on the left and on the right, coming in from the left, coming in from the right, both directions I'm approaching a value of 2. If I asked you simply for the function value at 2, then in that case I would be looking for the y value of the function at that x. So in this case, the answer would be -2. A common mistake is to confuse the value of the function with the value that the function is approaching. Now, we can directly plug in a value if the function is continuous at that x value. There are many graphs that we've learned about where the function is defined everywhere. So if the function is defined, we can say that if f of a is defined and it's continuous at that point, then the limit as x approaches a of f of x is equal to f of a. Simply saying that we can just plug that x value into the function. Now, up here, my limit does not exist if the limit as x approaches a from the left is not equal to the limit as x approaches a from the right. If no direction is given, then that means I'm talking about the overall limit where I have to compare the left and the right. Now there's going to be times when I don't have a graph handy and I cannot directly plug in my value to find the limit. So the question is, how do we simplify? Well, we learned several strategies. The first that we learned was that I would factor and cancel. Then we talked about how I could multiply by the conjugate. And then lastly, we talked about how I could rationalize. Now, all of these methods are done to basically allow us to rewrite the equation in another form where I can now plug in a given x value. All right. Next up is what happens as we approach a vertical asymptote. I'm going to draw a couple pictures for you here. So the first one is going to be our graph for f of x equals 1 over x minus 2 squared. In this case, we should be able to recognize that there's going to be a vertical asymptote at x equals 2 because that's where my function is undefined. If I were to just plug in test values, we would plug in values on the left and on the right of my asymptote, I would see that no matter what I plugged in, my y value is positive because my parentheses is being squared. And I would get a graph that looks like this. So as I am approaching my asymptote from the left or from the right, I am approaching infinity. So I could say the limit as x approaches 2 from the left of my function is equal to infinity. The limit as x approaches 2 of the right of my function is equal to infinity. And since those are the same, then the limit as x approaches 2 over all of my function is also equal to an infinity. Now let's say I had a different problem, and let's say I had g of x is equal to 5 over x minus 2. Now in this case, I still have the same vertical asymptote, so this graph would also have a vertical asymptote at x equals 2. However, because my factor is not being squared, as I plug in values around that vertical asymptote, I'm going to see my graph not always being in the same regions. So if I plugged in 1, for example, I would have a y value of negative 5. And so that would have my graph looking like this. If I plugged in 3, I would have a y value of positive 5. And in that case, my graph would look like this. So if I were to ask you the limit as x approaches 2 from the left of g of x, well, from the left, my graph is going down to negative infinity. If I were to ask you the limit as x approaches 2 from the right, on the right, coming in from the right like this, my graph is approaching positive infinity. Since these are not equal, the overall limit as x approaches 2 from my function does not exist. Now, if I'm asking you to take the limit as x approaches infinity or negative infinity, we want to ask ourselves what kind of function we are dealing with. If we are dealing with a rational function, like the 2 that I graphed above, then my limit will approach the value of that horizontal asymptote. And we find a horizontal asymptote by comparing the degrees of the numerator and the denominator. So for example, if my function looked like this, like the one I saw above, 5 over x minus 2, since the degree of the numerator is less than the denominator, then my horizontal asymptote is automatically at y equals 0. That's if the degree of the numerator is less than the degree of the denominator. If my function happens to have equal degrees on the numerator and the denominator, then my horizontal asymptote will be at the ratio of their coefficients. And that's when my degree of the numerator is equal to the degree of the denominator. And if it turns out that the degree of the numerator is greater, then in that case I would have to take a look at how my oblique asymptote would behave. So if I were to look at, for example, this g of x right here, if I asked you to do the limit as x approaches infinity, since this graph has a horizontal asymptote at 5/3, then as we head off into infinity, this graph will approach 5/3. Because what's happening, and if we look back up at the graphs above that I drew, what's happening is as my graph extends to infinity, my y values are approaching that horizontal asymptote. It's going to taper off at that horizontal asymptote. All of the action is occurring around that vertical asymptote. Now, if my graph is not a rational function and I'm dealing with a polynomial, well, in that case, I want to focus on my end behavior. And end behavior, if we have an even degree or an odd degree, and if my lead coefficient A is positive or my lead coefficient A is negative, then when it's an even degree, my graph goes the same direction on both ends. So if A is positive, it's up, up. If A is negative, it's down, down. If I have an odd degree, my graph does the splits. So if A is positive, it goes up to the right and down to the left. And if A is negative, it goes down to the right and up to the left. So as I'm taking my limits, if I'm approaching a vertical asymptote value, then I want to look at what my graph does around my asymptote. If I'm approaching infinity or negative infinity, then I either want to look at what is my horizontal asymptote doing, or if I'm working with a polynomial, what is the end behavior for my graph. When looking at continuity, there are 3 different types of continuity we expect you to be able to recognize. The first is jump discontinuity, and if we look at this graph pictured to the right, I can see that there is a jump discontinuity at x equals 0. My graph literally jumps from one piece to the next. The next type we see is point discontinuity, and that occurs right here at x equals 1. And we have point discontinuity because there is literally a point of my graph missing. Now, if I were to have a vertical asymptote drawn in here, I don't, but let's just say that I did, then I would have an infinite discontinuity at x equals -2. So even though a limit may exist because it's approaching the same value, there would still be a discontinuity there. Now, when we're trying to determine if a function is continuous at a point, there are three things that we have to verify. First of all, we have to show that the function value at that point is defined. Secondly, we have to show that the limit as x approaches that value is defined. And then lastly, we have to show that those two are equal. So we have to show that f of a is equal to the limit as x approaches a of f of x. Alright, time to move into derivatives. When we talked about derivatives, we first learned about how to take the derivative by using the limit definition. And the limit definition said the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now the final is multiple choice, so you're not going to have to walk through any of those long proofs. However, you should still be comfortable with the formula in case there are any questions asking you what formula you would use to find the definition of a derivative. Now, the derivative, what it represents is it represents the slope of the curve f of x at a given x value. And there are a couple times when our derivative is not going to exist. The times when we saw that the most was when the function is not continuous, and we just described it continuity a minute ago, or if there are sharp corners. And when we see sharp corners, many times our graph is still continuous. However, the reason why the derivative doesn't exist there is because the slope on the left and the slope on the right are not approaching the same value. So an example of a sharp corner would be, let's say we had an absolute value graph, the vertex, that v is a sharp corner. Or if I had a piecewise function, even though my graph is continuous and there is no gaps, that connector point is considered a sharp corner. When we are asked to write the equation of a tangent line, we're going to use point-slope form. And point-slope form is y minus y1 equals m times x minus x1. And the slope is going to be f prime of x, that is the slope of the curve at that given x value, and the ordered pair is going to come from the original function f of x. So basically what we will do is we will either find the slope from looking at the graph or from using the derivative equation, and then to find the ordered pair, we would plug that x value into the original function f of x, or find the ordered pair on the graph. When we are doing basic power rule to take the derivative, what we are going to do is we will multiply the coefficient by the exponent and then decrease the exponent by 1 for each term. So for example, if I was given the function 12x to the 4th plus 6x squared plus 3, and I wanted to find my derivative, I would do 4 times 12, which is 48, and then decrease the power by 1, so 48x to the 3rd plus 6 times 2 is 12x, and then the derivative of a constant is 0, so that term gets eliminated. Now, chain rule basically allows us to do a variation on power rule when the term that has the exponent is more complicated than x. So what we're going to do is we are first going to apply the power rule to the outer layer. Then after we've done that, we are going to multiply this answer by the derivative of the inner layer. So to show you what I mean, let's say I gave you the problem f of x equals square root of 7x plus 12. First of all, we want to represent this as something raised to an exponent. So I'm going to rewrite this as quantity 7x plus 12 raised to the 1/2 power. Now my power rule says that to take the derivative, I'm going to take this exponent, multiply it in the front, so I'll have 1/2 times quantity 7x plus 12, decrease the power by 1, so negative 1/2, and then now I need to multiply it by the derivative of the inside. And the derivative of the inside would just be 7. So this right here is the derivative of the outer layer, and this part right here is the derivative of the inner layer, the 7x plus 12. And then at this point, I would then check your solutions and determine how much you need to simplify the answer. In many cases, we could leave our answer like this. Sometimes we would need to go further. When we talk about rate of change is basically another way that we can talk about our slope. And we talked about how our position equation is represented by s of t, and the derivative of that, s prime of t, is equal to our velocity equation. So it's the velocity of the particle or item or whatever it is that is moving at a given time t. Now we talked about the difference between average velocity and instantaneous velocity. Average velocity, what we are going to do is we will get 2 position points from our position equation s of t. Then once we have those 2 points, then we will find the slope between them. Some examples that we gave in class for average velocity would be like your average speed after you drive for 3 hours, or after you ran 6 miles and you figured out, okay, I ran for 50 minutes, 50 divided by 6, and that would give you your average speed during your run. Now instantaneous velocity, this is kind of like your speed or your velocity in an exact second. So this is your exact speed or velocity at a given time t. So in order to find this, we would plug t into your derivative equation. In terms of comparing this to our driving analogy, this is kind of like if you see a cop and you look down at your speedometer and you see, oh boy, I'm going 80 miles an hour right this second. The cop does not care what speed you averaged over your trip, they care about your speed right then. Okay? If we are trying to figure out average velocity from a graph, we would get those 2 points and then calculate the slope between them. If we were trying to figure out instantaneous velocity from a graph, we would have to find the slope of the curve at that point. All right, that's it.